Hi. In this video, we will be talking about damped oscillators. So yeah, we will be talking about damped oscillator. So what happens is that in earlier we have talked about simple harmonic oscillator. We have talked about simple harmonic oscillator, and the differential equation for simple harmonic oscillator can be given as mx double dot plus kx is equals to 0, where x is a function of time, and solution to such equation is given as your a sine of omega t plus phi, where your omega is equals to under root of k by m. So this is quite the solution of simple harmonic oscillator. But there's one thing about simple harmonic oscillator is that in time, so the energy remains constant. So there is no decrease in energy over the time, and so the energy remains constant. So what happens in principle is that if you have this bob, let's say, have this pendulum, and if you release it from here, let's say, so every time this pendulum will oscillate like this. Okay, fine, it got a little bit bent. Yeah, something like this. Yeah, so every time this will oscillate, and if this is the theta naught, that is your initial angular displacement, every time in each and every oscillation it will regain this theta naught. But that's not quite the realistic case, because what happens is that over the time your theta naught will decrease. Your theta naught will decrease. And one more thing about this model is that this is quite a what would I say, is quite idealistic model. It's a quite idealistic model which do not account for stuff like friction or drag. So the two things which are friction or drag, they need to be counted, so they are not accounted by this equation. So what we will do is we'll talk about a new model. We'll improve our model so that we can account these two things also in our model. So what I'm going to talk about is what we call as the damped oscillator. So what happens is that in damped oscillator you have a frictional force that is given as minus of BV. So where your B is called as your drag constant, and your V is the velocity, and your V is the velocity. Right, so if I were to write the equation of motion for this thing, so it will be given as mx double dot plus bx dot plus kx is equals to 0. So this is the differential equation for a damped oscillator. This is the differential equation for a damped oscillator. Now let's try to solve this differential equation to get the solution. So what I will do is I divide the whole side by m. So it will be x double dot plus bx dot divided by m plus k by m, x equals 0. So what I do is I put this b by m and k by m. I will replace them with some numbers, with some new variables. Let's say it's beta, and let's say it's omega naught squared. So this differential equation will in turn turn into something like this. That's given as x double dot plus beta x dot plus omega dot squared times x. Right. Now, so this is my differential equation which I need to see or solve. And the first thought which comes into my head that what could be the possible x? What could be my possible function? Well, what could be my possible function which will satisfy this equation? And well, the idea says is that the second derivative, the second derivative on the first derivative has to be the function itself. So in a sense, it has to be the function itself. So one of the possible solutions which comes to my head is I propose this solution that x, the function of time, is given as c e to the power lambda t. So I say this is the solution, and now I will put this solution to this differential equation, and get the things wrapped around it. So x double dot as a function of time will be given as c lambda squared e to the power lambda t. X dot as a function of time will be given as c lambda e to the power lambda t, and x as a function of time is given as c e to the power lambda t. And now let's put all these things into this differential equation, and what I will get is c lambda squared e to the power lambda t plus beta c lambda e to the power lambda t plus omega naught squared c e to the power lambda t is equals to 0. Now let's take out e to the power lambda t, so c e to the power lambda t common. So c e to the power lambda t, that's given as lambda squared plus beta lambda plus omega naught squared. So that's got to be 0. And yeah, so now what could be the possible ways in which I could get this equation satisfied? So one thing could be that my c equals to 0, but that's quite a weird solution, because it says that it's 0 for all times, but I mean, such solution gives me no idea. I mean, it's nothing actually, in a sense, if I say so. It's a bizarre solution, so I just neglect it, right? And for this e to the power lambda 2 to be 0, if t approaches to minus infinity, this is again 0, but also that this thing is true only at or approaching to minus infinity or very near to minus infinity. This thing will go to very, very close to 0. So this is also not true. So what happens is that for this differential equation to be true at all times, or for the solution to be the solution for all times, I would set this thing to 0. And if this thing is 0, then it works for every time. So what happens is that we are lambda squared plus beta lambda plus omega dot squared equals to 0. So I will use this quadratic formula. So it gives me lambda equals to minus of b minus of beta plus minus of under root of that is beta square minus of 4a c, that is 1, and omega naught square divided by 2a. That's the solution. And yeah, so what it comes out to be, that's lambda is equals to minus of beta plus minus of that's given as under root of beta square minus of 4 omega naught square, that's divided by 2. So what could happen is that there could be two solutions. So one could be, let's say I take lambda to be minus of beta plus under root of beta squared minus of 4 omega naught squared. This whole thing is divided by 2, and I take lambda to be minus of beta minus of under root of beta squared minus of 4 omega naught squared divided by 2. So I take up these two values and I can find two solutions. So my first solution, let's say x1 of t, is given as c1 e to the power exponential of minus of beta plus under root of beta squared minus of 4 omega naught squared, and this whole thing goes divided by 2. And x2, that's the second solution to this problem. X2 as a function of time could be also given as c2 exponential of minus of beta minus of under root of beta squared minus of 4 omega naught squared divided by 2. Yeah, one thing I forgot here is t. Sorry, is t. Yeah, sure. So it's t, right? So these are the two solutions, and what we know that the linear combination of them will also be a solution. So if I want a more generalized solution, so x as a function of time would be given as c1 exponential of minus of beta plus under root of beta squared minus of 4 omega naught squared. This whole thing goes by 2 times t. Okay, and let me move it somewhere a little bit. I need some space. Yeah, and plus c2 exponential of again minus of beta minus of under root of minus of beta squared minus of 4 omega naught squared divided by 2 t. And so yeah, so here we go. This is quite my solution to the problem. Yeah, just a second. I hope it works. Yeah, so this is the solution to the differential equation. So this is the solution to the problems, but so by putting the values of appropriate t, now you can get the solution. You can get their position at different times, right?